Now we're going to talk about gases. A quick reminder about the states of matter. Solids have set shapes and set volumes. Liquids have set volumes but no set shapes. And gases have neither set shapes nor set volumes. So this is, as far as the very common ones, the least organized part of matter. But there are some effects with them. Let's first talk about straws. How long is too long to have a straw to drink soda? And the answer is going to be 10 meters or 33 feet. You can't, at least at sea level. So how long does it take? How does the straw work? Well, what you do is you pull the gas outside of the straw, and then the atmosphere actually pushes it down. So and we talk about the pressure, the atmospheric pressure. Where does that come from? Pressure is a force per area. And for the atmosphere, the average part of the atmosphere, at least here at sea level, it's 101,325 newtons per meter squared, and that's known as a Pascal. That is the force of a Pascal. Maybe you've heard of 14.7 psi, pounds per square inch. That's another one that we use quite a bit. Atmosphere is the average pressure of the atmosphere. We also have millimeters or inches of mercury. We'll talk about that later. These are all pressure units. And so the way that straws work is when you pull the water outside or pull the air outside of the straw, the atmosphere itself pushes down on the liquid and draws it up the straw. And this will work fine as long as the height of the liquid that you're pushing, and I'm assuming the liquid is going to be water. It's the height of whatever liquid is you're drawing is the way that pushing down is less than the force from the atmosphere. And for water at sea level, it's going to be about 10 meters or 33 feet. Also, for certain things like this, if you want to become a firefighter, for instance, or if you're going to be engineering and working on things like pressure going up in a building, there are engineers that work on the water pressure throughout a building, and the general rule is 33 feet is 15 psi. I know it's 14.7, but that's kind of what they teach people for like the off the cuff calculation. So, and it means say you're a firefighter and there's a fire that's up 100 feet, how much pressure should you put in the pump? Well, 33 times 3, 15 times 3, so you need 45 psi of pressure on the hose line to shoot water 100 feet, for instance. So that's something they teach you like I said, as a firefighter. And similar to how big of a pump should I make to push water up a building so the toilets will flush on the top floor? Well, you have to look to see how high the building is and then work about 33 feet per 15 psi is typically what's done for engineering and buildings. I mean, of course, everything is checked with software and all that kind of thing, but if you want a general idea, and that's kind of like the engineers, it's like, oh, okay, that's kind of makes sense about that. That's kind of the ratios that they go through in their heads. So let's talk about kinetic molecular theory. So this is a model for gases. We keep on talking about models, right? We're so full of models, and that's the other thing about general chemistry. We change topics so much. This is a tough class for you guys, so I appreciate your attention for so long as we go through so many different topics. We'll talk about kinetic molecular theory, and it describes a perfect gas. So we describe what a gas is, and it does break down. So an ideal gas is based off of the kinetic molecular theory, but we'll talk about that. And generally speaking, for this temperature and pressure, meaning I'm now at about 28 degrees Celsius and 1 atmosphere pressure. Ideal gas law and kinetic molecular theory work very, very well for this. There's very little error. Kinetic molecular theory does not work well under cold conditions and really high pressures. So higher temperature, lower pressure conditions, and sea level of the Earth is considered those. And pretty much any time that humans are going to be alive, it's considered low pressure and high temperature. So it works for us in our own lives pretty well. But I mean, if you're dealing with industrial processes, then maybe not so much. So this is kinetic molecular theory. The particles are always in a constant motion. All collisions are elastic, meaning they don't stick. There's no attractions. There's the part three, the space between the particles compared to the size of the particle themselves. Essentially, gases have no volume. The gases have a volume, but the particles that make up a gas have zero or negligible volume, meaning that this does not come into play. And then four, and this is a true definition for everything. The speed of the particles increases with increasing temperature. I mean, that's a definition of temperature. Actually, it's average translational kinetic energy. So four is just the definition of temperature. So gas, more or less, they move in a straight line, but they're bouncing all around. And there is no attraction or repulsion. They just kind of bounce around, bouncing each other, and they go back and forth. And they have the particles themselves have negligible volume. And then four is just the definition of temperature. So this is all what we said before. And something else with the gases are compressible. So solids and liquids, they're slightly compressible, but not to any appreciable amount. So, and if you've ever gotten air in your brake lines of your car, you know this, you push on the brake and then nothing happens. But then if you have the brake fluid and no air, then the hydraulic action of that works really well. And generally speaking, also gases assume the shape and volume of the container. That's because that's what gases do. They have neither set shape nor volume. They just assume the volume and shape of the container that they're in. And gases, generally speaking, are relatively low in density and mass per area. So density, grams per cubic centimeter is typically what we do for density. So the density is pretty low. So gases are compressible, liquids are not, as aforementioned. And gases assume the shape of the container, right? And gases relatively have a low density. So to give you an example, density of steam at 1 atmosphere pressure, 100 degrees Celsius, is about 0.0006 grams per cubic centimeter. Liquid water is 1 gram per cubic centimeter, so it's less than 1/1000th, right? So that is very, very small. So gases, generally speaking, do not have nearly the same amount of matter in them per volume as liquids and solids. And liquids and solids are also referred to as the condensed phases, and gases are referred to as the vapor phase. So what is pressure? Pressure is the result of the momentum in the collision. So you can punch the wall with your fist, and that's a force, and it pushes over an area. But what if your fist is the size of a gas molecule? So it's a much smaller, mass. But if there is a whole mole of those pushing up against something, those collisions and hitting the wall, the sum up of all of that is where pressure comes from. So, and there are a little bit of variations in the atmospheric pressure, but there is more or less an average amount of it. But of course, when you go ascend in altitude here on Earth, generally speaking, the pressure goes down. So, I mean, there might be a little bit of perturbations here and there, but generally speaking, the higher you go in the atmosphere, the less pressure there is. So, and also we're in equilibrium. So there's an equilibrium pressure both inside of us and outside of us. And when it changes, you can feel it, the equalization that you want to happen in your ears. So, and I already mentioned that. And this is the structure in your ears that help balance that in the eardrum there. So, and of course, opening your mouth and kind of clicking your ears, or for me, I chew gum like in an airplane. That seems to really help and make my ears feel better. Otherwise, you can get pain. So pressure is a force per area. That's a definition of pressure. And it's the sum of all of the collisions of the gas over the container. So, and since we have such a huge number, even though there's a little bit of momentum there in each of the particles, if you sum them up over all of them, it turns into something you can actually recognize. So it's a big problem to sum up all of that. And then the pressure. So we're going to build up now to the gas laws, but let's talk about some things with a given volume. If you have the same volume and you add more gas particles, that means that there's going to be higher pressure. So the amount of gas is directly involved in how much pressure there is. And so units of pressure, we talked about a little bit before, the SI unit for pressure is Pascal. It's the force of a Newton over a square meter. Newton is not a very strong force, and a square meter is a pretty big area. So we have other units. We typically use millimeters of mercury in as far as pressure, and this is partially because we used to use manometers. That was a way of looking at so it's a glass tube in the shape of a U, and you have mercury in it, and then the height of the mercury changes, and you could look at the pressure differential by the height of the different of the mercury, and you could take a meter stick and measure the difference in millimeters, right? So that's the old school way of doing it. Of course, now we usually use electronics and typically diaphragms or whatnot to measure pressure. An old school barometer is this image here, and barometers we typically say it in inches of mercury, and about 30 inches of mercury is an atmosphere of pressure. And you might even hear the term the mercury is falling. When water condenses, the atmospheric pressure suddenly drops. So if you see a sudden drop in atmospheric pressure, that usually means it's about to rain. So you might hear that on the radio. I hear that sometimes people listen to the radio, and the mercury is dropping this morning, and then like, what does that mean? It means it's going to rain. So here are some units. Again, an atmosphere is 760 millimeters of mercury, and we can also use millimeters of mercury and torr interchangeably. And it's named after the physicist who invented the barometer. And we can also have about 30 inches of mercury as an atmosphere, and also 14.7 psi for an atmosphere. So these are all interchangeable units to 1 atmosphere of pressure. So there's another unit here we didn't talk about, the bar. The bar is 100,000 pascals, or 100 kilopascals. That's a unit of measurement used more frequently in Russia and the former Soviet Union. And I must admit, the one thing that they have better than we do, our standard states are at 1 atmosphere and theirs are at 1 bar. So theirs actually are better engineered than ours are. So we still use an atmosphere, but Russia uses a bar for their average for their pressures of their standard states. So common units pressure, we already mentioned this here. And unit conversion, so atmospheres to millimeters of mercury, it's just you're multiplying by 1. So how many millimeters of mercury is 0.311 atmospheres? Well, this is a direct calculation here, unit conversion, 236 millimeters of mercury. And airplane cabin pressurization. So I have this problem. I do not do well at altitude. Anything over 8,000 feet makes me feel kind of crappy. But at 25 to 40,000 feet, atmospheric pressure is much lower than here on the surface. And having low oxygen in the atmosphere, it does not feel good. Dizziness, headache, shortness of breath, and can even go unconscious. So for me, myself, my emotions kind of go away. It's kind of weird being emotionless. So what do we do around this? They pressurize the cabins. And if the cabin loses pressure, oxygen masks will be deployed for the comfort of the people. What happens actually in the airplane, they will descend to 10,000 feet. And although that is, most people are okay at 8,000 feet, 10,000 feet, most people are still okay. So, and it takes a while to go down to 10,000 feet though. So it's, you don't have to breathe for long, but it is nice to have. I've never been in an airplane and experienced that. So, and I hope to never feel that. So, it has to do, the pressurization works by compressing the air as it goes around. And this pressurized air also creates a thrust that drives the plane forward, but it's also from the combustion of the jet fuel. So it's also this pressurized air, but it's also there's a combustion reaction that happens. So, and this is they more or less keep the minimum, and this is they're not allowed to go lower than this 8,000 feet. The old equivalent of 8,000 feet. Some planes have less than that, so the larger planes, the 777s and the 767s, these tend to pressurize closer to 6,000 feet. And to be honest with you, I prefer to fly in those jets than the tinier ones. So let's talk about the different kind of gas laws, and these are laws, summary of observations, and we're going to build up to the ideal gas law. So start with Boyle's law. Boyle's law basically says pressure and volume are inversely proportional. So which means is if you increase the pressure, the volume goes down, or if you decrease the pressure, the volume goes up. And this is for a given temperature and amount of gas. And you can look at the other way. If the volume decreases, the pressure goes up, or the volume increases, the pressure goes down. So which means when one goes up, the other one goes down. That is known as inverse proportional. And this is described as V for volume is proportional to 1 over P for pressure. That symbol there is a lowercase Greek letter alpha, and it means proportional to. So that means volume is proportional to 1 over P. That's also known as inverse proportionality. When one goes up, the other one goes down. And this another way you can look at it is the multiplication of pressure times volume equals a constant. So you can also look at it as P1 times volume of 1 equals P2 times volume of 2. So let's look at this idea. So if you have a J tube, which is, that tube is in the shape of the letter J, and you seal the end, and you can see the height difference here. If you pour more mercury into that, the volume is going to go down because it's increasing the pressure. And with this, the volume versus pressure, you can see that is an inverse relationship where you increase one versus the other. And like as you asymptotically approach the origin, the volume goes towards infinity, and as you asymptotically approach zero volume, the pressure goes to infinity. So that's an example of of inverse proportionality. So let's look at it in the molecular view. So you have something is pushing on, the gases are pushing on things, and you have a weight over a piston. And so what happens when you put more weight on that piston? Well, then the volume decreases, and it keeps on going until that same number of gases at the same temperature will then reach an equilibrium where the weight of that force will be counteracted. So this is an idea. That's how that works on a molecular level. So let's talk about scuba diving. We talked about airplanes. Let's talk about scuba diving. So remember that 10 meters of water equals about an atmosphere of pressure. So if you're on the surface of the ocean, the pressure that you experience is 1 atmosphere. Then you go under 20 meters, so go down about 66 feet. And now that means the pressure, you get 2 additional atmospheres of pressure from the water, plus the atmospheric pressure from the atmosphere. And now you have a total pressure of 3 atmospheres. So you have to be careful with this, and there are certain effects with this. So meaning when you do this, you have to keep in mind that the pressure is actually more than what you expect. And then let's look at the other way around. If you ascend too quickly, so if you are going up at 20 meters, there's a pressure of 3 atmospheres, and then you ascend to the surface, the pressure is now 1 atmosphere. So you have to either go up slowly and breathe, or exhale the whole time you go up. Otherwise, that can cause really bad damage to your lungs. So, and if there is an issue where you have to ascend quickly, breathe out. I don't scuba dive, so I've never had this happen to me. But this is This sounds pretty scary. Right. So, all right. So Boyle's law. So here, let's a problem of Boyle's law. So looking at this problem here, a cylinder equipped with a movable piston has applied pressure of 4 atmosphere. The volume is 6 liters. What is the volume of the cylinder when the applied pressure is 1 atmosphere? So we have so one equation, one unknown. So we have our first pressure, first volume, second pressure, and what is the second volume? And not included, you assume that there's constant temperature and number of moles. So we're going to use this equation, and then looking at the equation, then solving for the unknown variable, in this case V2, right? So we divide pressure 1, volume 1 by the second pressure, put in the numbers, and we get 24 liters. So the second volume is going to be 24 liters. And does this make sense? Well, you decrease it by a factor of 4, so you're going to multiply it by a factor of 4, and the 6 liters, 6 times 4 is 24, so yeah, that makes sense. So another one, a snorkeler takes a syringe with 16 milliliters of air from the surface, and the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe is 7.5 milliliters. What is the pressure at this depth? And assume 1 atmosphere for every 10 meters depth. How deep is the snorkeler? So we have to find, so 2 parts. First thing we have to do is find the second pressure. And so we find the pressure to be 2.1 atmospheres. And don't forget, though, that 10 meters of water is equal to about an atmosphere. So there's the extra depth of 10 meters. I'm sorry, the extra pressure of 1.1 atmosphere. So times 10, that's 11 meters. So that's where these numbers come from. And back in the day, I didn't even watch these cartoons, and I'm old. So the Flintstones came along, and the main characters are snorkeling, and then they have these really, really long snorkels. And would this work? Would this really long snorkel work? The issue with this is if you try and breathe. So here, if you're 20 meters underwater and your lungs have a pressure of 3 atmospheres, and you're trying to draw breath from a pressure of 1 atmosphere, problem is, so let's talk about flow. We don't talk about flow very much in this class. We do talk about heat flow. Heat always flows from hot to cold. So gases flow from high pressure to low pressure. So if you try to breathe at 3 atmospheres and the to an area that has 1 atmosphere, what's going to happen is your lungs are going to collapse because gases flow from high pressure to low pressure. So that means if you try and breathe at that, it's going to collapse the lung. So it is not possible to breathe. So another question, why does hot air rise? Well, it's because when air heats up, the volumes expand, the density goes down. And when density goes down, then the cold air above it, by a field of gravity, pulls it down, and then the hotter gas goes up. So it's not necessarily cold air, and the hot air rises. It's really, to me, I think of it as cold air sinks. But hot air does rise, and that's from what's called the buoyant force. It's the amount of whatever material you're displacing. And but with that, increasing temperature increases volume, and this is Charles' law. So hot air balloons work like this, and you see hot air balloons, and that's a big amount of air. There's not a lot of matter in air, so right, if you want to float in water, I float in water, and like my body and I'm pushing enough water out of the way that my head is above water. So all right, and if I want to make sure I float, I keep my lungs really full of water, so I displace more water. So you can see that how big of a volume of air you have to push away so that you're able to float away. So air is not very massive, we compare that to water, right? So if you displace water, that's how things and displacing water, that's how you have like, ships can stay afloat in the ocean and whatnot. So here's Charles' law, and you can see it's a direct proportional. So remember, Boyle's law was inverse proportional. This is direct proportionality. And we have temperature and volume. And you can see that it follows a straight line. And we're going to extrapolate. And we find that it crosses the origin at negative 273.15. So 273.15 degrees Celsius. And we also refer this to the zero volume of an ideal gas. And it's also known as absolute zero. So absolute zero, definition of temperature is average translational kinetic energy. So absolute zero is also when things stop moving in reference to space-time. So they can still rotate, they can still vibrate, they can still have quantum uncertainty, but they are not moving along the three Cartesian coordinates, x, y, z, right? So they are not moving, they are staying put as far as translational motion. And at that point in time, we call that absolute zero. And from that, it means you can't get colder than absolute zero. I remember I was a judge of a science fair, and there was a child said, and I extrapolated data, it was negative 10,000 degrees. And so I tried to explain to the student that it's impossible to get below absolute zero as far as coolness. So you can't get colder. You can't get colder than not moving. So that's the absolute zero. So temperature is actually an absolute scale. Temperature is also a measure of energy. It's the average amount of energy, and so we can tell by how much energy we put into the systems. We can calculate that down, to joules, and you learned about that when we were talking about in the previous chapters and talking about the heat capacities, right? So we can calculate that, and temperature. Temperature is an absolute scale, and it is something absolute scale meaning it's not relative. So like Celsius, for instance, is a relative scale. It's based off of freezing and boiling of water, and but absolute scale, Kelvin temperature, you have a zero temperature, and that's when things are not moving. So Charles' law found this out, and he found out that volume was directly proportional to temperature, which means when volume goes up, temperature goes up, and when temperature goes up, volume goes up, temperature goes down, volume goes down, volume goes down, temperature goes down. They're all directly proportional. That's what that directly proportional means. And so, for instance, here you have a consistent pressure, consistent amount of gas. So you throw a balloon of water into the freezer, it's going to shrink. You put it in boiling water, it's going to get bigger. So that's how volumes change. And one of the so whats for this, of course, is that sometimes, depending on the ambient temperature, you may have to add or take air out of your tires of your car to have the more idealized pressure for gas mileage. So here's Charles' law. You can look at it as V1 over T1 equals V2 over T2, or V1 over T1 equals a constant. So, and temperature also needs to be expressed in kelvins for this to work. So Celsius will not work. That is a very common problem students have. They do not use the absolute temperature. They use the Celsius temperature. So let's look at an example of this. A gas has a volume of 2.8 liters at some unknown temperature. When the sample is submerged into ice water at 0 degrees Celsius, its volume decreases to 2.57 liters. What is the initial temperature in Kelvin and Celsius? Assume a constant pressure. So we are given this information. We are given two volumes and two temperatures. We don't know the initial temperature, but we know the second temperature is going to be 0 degrees Celsius. So we look at the solution map, and then we solve. We solve for the initial temperature. So you solve for, well, you start with this and you solve for the initial temperature, and I guess they missed the one of the parentheses here. So it's going to be T2 times V1 divided by V2 is the temperature. And make sure, convert to Kelvin. So the 2 degrees Celsius is 273 Kelvin. And then you plug that into the derived equation there, and you get 297 Kelvin. So minus 273 is then 24 degrees Celsius. So that's how you can figure this out. So let's combine Boyle's law and Charles' law together to get the combined gas law. You can take the different ones and combine them together, and you can use this to solve problems. So a sample gas has a volume of 158 milliliters, pressure of 735 millimeters of mercury, temperature 34 Celsius. If the gas is compressed, has a volume of 108 milliliters and temperature 85 degrees Celsius, what's the final pressure? So use the combined gas law, and from that find P2. So we have all the variables noted, and we're missing one of the variables. So we solve for P2, and remember temperatures in Kelvin. So starting with the combined gas law, solve for P2, put in the numbers to get the proper temperature, and then put in the values there. And notice that the units cancel, and we're left with 1,250 millimeters of mercury is the answer. So that's a pretty hefty pressure. So it must not have been in air. It must have been under something in a reaction vessel or something. Okay, so Avogadro's law. Avogadro's law says that the volume of a gas increases proportionally to the number of moles. So Avogadro's law, and you see we're building up the different laws, and this makes sense though. This makes sense because if you've ever blown up a balloon, how do you blow up a balloon? You add more air into the balloon. So adding more air in the balloon then tells you, oh, it's blowing up, right? So, when you blow up a balloon next time, think, oh, that's Avogadro's law. And also when you let the balloon go and it zips around the room, think, aha, Avogadro's law again. So can't miss Avogadro's law. So let's look at an example here. 4.8 liter sample of helium has 0.22 moles of helium. How many additional moles of helium do we need to have to obtain a volume of 6.4 liters? Assume constant temperature and pressure. So you're just filling up a little balloon full of helium. So we have our variables. We have 4 known and 1 unknown. We have an equation. So we have 1 equation and 1 unknown. So that means we can solve for it. So in doing so, we're going to look to the other amounts of moles. So the second amount of moles, so the top is of Avogadro's law. We're going to solve for the number of moles in the second one, and then we go through and we get 0.29 moles. I think, I'm done. But the problem asks for how many more additional moles of gas do I need to put in? Like, oh, no. So we initially had 0.22 moles, and we need 0.29, so we have to subtract the 0.22 from the 0.9. So the final answer is 0.07 moles. So that's where you have to look to the problem and keep to thinking about it. So we're going to move on and talk about the ideal gas law. And the ideal gas law combines all the other laws. And then we're going to come up. The other thing is we suddenly have this new value R. So what is R? R is known as the gas law constant. R is actually the Boltzmann's constant times Avogadro's number. So if you're wondering, actually R is 2 other constants. The ideal gas law is actually a mathematically derived law. So it's really a mathematically derived law, and it's based off of kinetic molecular theory. So this is one where it's just plain out derived using basic principles in math. And the Boltzmann constant is something that deals with proportionality and probability. And the value of R is 0.08206 liter atmospheres over mole Kelvin. And so one of the things with R, it depends on, you will see the gas law constant in other forms. R can also have the terms 8.314 joules per mole Kelvin. So depending on the units, so be very careful over which value of R you use. So make sure that the units all work out. So that's for other problems involving R. And R, as I said before, it's really the Boltzmann constant times Avogadro's number. And so using, and R changes also if you change the units. So looking at this value of R for units, pressure is in atmospheres, volume is in liters, moles of gas is in gram moles, and that's the one that we use for Avogadro's number. There's also pound moles and kilogram moles. We've only been using gram moles. Temperature must be in Kelvin. So let's look at this. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a pressure of 315 Kelvin. So we have three knowns, and what are we going to do? We're given three terms. Well, we can have the ideal gas law. And R is a constant, we always know that. And we know the number of moles, we know the pressure, we know the temperature. From that, we can solve for volume. So we're going to take the ideal gas law and divide both sides by P to get the volume. And then we put in the values for that we know. And remember, R is a constant. And notice that the units all cancel out except for liters. And at the end, we're given 16 liters. So that's how you do this problem. And to check the answer, I typically go and kind of see, oh, does that make sense? Is that going to be about right? We haven't talked about something, but we have a mole gas occupies about 22.4 liters. And so if looking at these terms, so a little bit higher temperature, so it means it's going to be a little less than that, and then higher pressure. So if it's on the order of 20 liters, it's probably right, and this is on the order of 20 liters. So that's like, in my mind, I would say, okay, this has got to be close to that, and this does make about sense. So that's what it's like, does something make sense? And that's kind of like, for me, I would guesstimate, it would be a little bit less than 22.4. It'd be like 20-ish. And then we're getting 16. So I'm like, yeah, that makes sense. If I got like 2 liters, I'm like, I don't know. If I got 100 liters, I'm like, maybe I did something wrong. So that's like when you kind of say, does this make sense? So we can do other problems, and you can see we're going through various types of problems. And one of the things, though, there are an infinite number of problems that you can be approached as a student. So we're doing this to try and hope that you see some commonality in the strategies here. I mean, here it's it's fairly algebraic, but also understanding the definitions of things, and then be able to take the data, what you're given and what you're asking for, and then kind of find a pathway. There is not really any pathway that works for everything under every circumstance. This is just something you have to think through each time. So that is one thing with this. So let's look at this. Sample of gas has a mass of 0.136 grams. Its volume is 0.112 liters, temperature 298 Kelvin, and pressure at 1.06 atmospheres. Find its molar mass. Well, we're given temperature, pressure, and volume, and from that, we can figure out the number of moles, and we know the mass, and the molecular weight is grams per mole. So we just have to take, the way we'd figure this out is we just figure out the number of moles and then take 0.136 divided by the number of moles. So let's solve for the number of moles. So PV equals nRT, that means N equals PV over RT. Plug in the numbers, and we get 4.85 times 10 to the minus 3 moles. And the molar mass is mass over moles, so 0.136 grams divided by the number of moles. And we get 28 grams per moles. And right away, actually, you would know this is nitrogen gas, because nitrogen is 14 times 2. So the gas is nitrogen. That's the other thing you could take from this. Or it's very likely to be nitrogen. So here's a summary of the different laws. And to be perfectly honest with you, I honestly just use ideal gas law. I typically kind of just forget all these and just deal with ideal gas law. That never fails me. So let's talk about when gases don't act ideally. So under low temperature and high pressure. So when things are low temperature, that means that there tends to be a little more attraction between the particles. And you can see in that image, they kind of start to hold hands, they kind of hang out together. And the problem is when two gas particles kind of hold hands like that, they kind of act like one unit instead of two. And for ideal gases, it doesn't matter what the gas is. It just the gas is the gas. It doesn't matter the identity of the gas. The gas behaves the same way as far as the pressure and temperature. It has to do with the number of particles, and this changes the way that the pressure and volume can express itself. The other thing with high pressure, if it's really high pressure, then if the gas particles get pushed so far together, the actual size of the gases themselves, like the atoms, they start to take like they are now a factor. We actually have the size of the matter itself, and gas is usually very diffuse, especially under ideal conditions, and that means, well, you know what, the particles are just they're just so much smaller that we don't really care about how big they are. But now, if it's under really high pressure, the particle size start to matter. So, let's talk about then a mixture of gases. So, really, for ideal gases, they don't interact any differently from each other. So, since they don't have any attraction for each other, really, it's going to be just the partial pressure, either the partial pressure or the mole fraction of it. So whatever fraction you have, and for gases, number of moles and pressure are directly proportional. So for instance, in our atmosphere, air is generally, at least, dry air, meaning no water vapor, 78% nitrogen, 21% oxygen, and a little less than 1% argon, 0.04% carbon dioxide, and trace a lot of other things. Water can vary, and we typically say this is for dry air because of that. So the largest we have is 78% is from nitrogen, and generally speaking, the nitrogen is fairly inert. It doesn't react as much. Argon even less. Oxygen is really important to us because we need to breathe, of course, and it's 21%. So let's look at other mixtures of gases, for instance. So we have helium and neon, and we're going to put 0.8 atmospheres of helium and 0.2 atmospheres of neon into a container. What happens? Well, they just the pressures just add, and then the fraction of it is just the total pressure, and then you can look at the percent gases just by the fractions of the pressure. So doing moles of gas is directly proportional to the pressure. Now remember, this does not work for weight. So helium is much lighter than neon, so this does not equate to weight. It only equates to number of moles and pressures, not mass. So Dalton laws of pressure is the total pressure is the pressure of species A plus the pressure of species B, and so on. So the total atmospheric pressure, for instance, is 0.78 atmospheres of nitrogen plus 0.21 atmospheres for oxygen plus 0.01 atmospheres for argon, and then the total of that equals 1 atmosphere pressure. And I mean, we're slightly inflating the pressure of oxygen and argon because there's other trace gases, but that is true for the most part. So let's look at an example here. We have a mixture of helium, neon, and argon, total pressure of 558 millimeters of mercury. The partial pressure of helium is 341, and the partial pressure of neon is 112. What's the partial pressure of argon? Well, we are given the total pressure and the pressure of two of the species. So we know the total pressure, but we don't know the pressure of one species. And remember Dalton's law, the total pressure is the sum of them. So we can solve for the pressure of the unknown argon. We take the total pressure minus the pressure of helium minus pressure of neon, and then we get the 105 millimeters of mercury. So pressure and physiology. So humans more or less are used to breathing pressures at about 0.21 atmosphere. So And but when this pressure decreases, we can get a condition called hypoxia, and we really do like it about this. This is kind of the limit. For some people like me, it happens at about 8,000 feet, and I have no ambition to climb Mount Everest whatsoever. So this is not for me. And mild hypoxia, it's not a very pleasant feeling, I can tell you that. Um, and when severe hypoxia, if it drops below a tenth of the atmosphere, you can be unconscious or even die. And people that do make it to Mount Everest usually carry oxygen. So on the other side, so high levels of oxygen also can cause bad effects. So you can breathe pure oxygen, for instance, and actually, if you're lying down and you're breathing pure oxygen, it feels wonderful. But you got to be careful because when the partial pressure of oxygen goes beyond 1.4 atmospheres, that will kill you. And I've never experienced this, but I'm told that you feel very anxious and you breathe very slowly. So imagine breathing very slowly and your heart pounding in your chest. So that's apparently what this condition feels like. I've never, like I said, I've never felt this way, but this is what can happen, especially if you are a scuba diver and you go too far down. And this pictorially shows you with, increase the depth, you can increase the partial pressure of oxygen in your blood. And if it goes beyond 1.4, you can get the oxygen toxicity. So good old moderation argument. So you need moderation, moderation, moderation. So you need too little oxygen is bad, too much oxygen is bad. And at about zero point 0.2 atmospheres, that's just right. So, and so what do we do? Besides oxygen, also you can get nitrogen narcosis. So beyond 4 atmospheres of pressure, so about underneath 100 feet or 30 meters, you can get nitrogen narcosis. And I've never experienced it, but apparently it feels great. You get high. So tipsy, and the thing is, judgment can be impaired. You can do stupid things, and people can make mistakes. So when you're working underwater, say you're in a job working and you feel like you're drunk, then that can be a dangerous thing. So what do we do? And people do go below 40 meters. You have to use a special mixture of gases. Typically, Heliox is used. It's a mixture of helium and oxygen, and so it lowers the amount of oxygen, and then nitrogen for 2 reasons. To eliminate nitrogen narcosis. Also, nitrogen can dissolve in your bloodstream, and you can get when you ascend, you get a condition called the bends, and it's like because there's nitrogen bubbles that form in your blood, and they collect around your joints, and it's very painful. Again, I've never experienced it, so. There's 2 reasons for using helium. Helium does not appreciably dissolve in the blood as much as nitrogen, and then you also don't get nitrogen narcosis. And so helium is just because it's not very soluble into water at all. Gases are slightly soluble into most gases. Some gases are very soluble, like carbon dioxide and ammonia, but the air, oxygen and nitrogen are not very soluble. They are slightly soluble, but not extremely soluble into water. So, and helium is even less so. So helium is a good combination gas to use with oxygen for deep sea diving. So to give you an example, calculate the partial pressure of oxygen the diver breathes with a Heliox mixture containing 2% oxygen, the depth of 90 meters, where the total pressure is 10 atmospheres. So the O2% is 2% total pressure, and that's total pressure. So 90 meters would be total pressure. It's going to be 9 from the water and then 1 from the atmosphere. So and I'm saying this because there's a difference between gauge pressure and absolute pressure. So Absolute pressure is the total pressure, and gauge is just what it says. So how do we solve this? The fractional composition is going to be 0.02. So that, and then looking then at the total pressure, then the 10 atmospheres. So the pushing on the blood is going to be 0.2 atmospheres. So actually this is perfect, right? So this is perfect. And actually the person with this mixture can even go down further, right? So maybe a little lightheaded as the person goes up, but it's going to be, by using the things here and the components, total pressures, this is a very good mixture. So it's close to what the person would feel at the surface. Vapor pressure, talk about briefly. So we model model liquids as having a pressure on the surface of it. And another thing is when we say that when the vapor pressure of the liquid equals the ambient pressure, the liquid boils. So, but let's look at this problem here. We have a test tube with a stopper in it that has a gas line into a container that we're going to collect the gas and measure it, and we want to see what the number of moles of hydrogen is in it. But the problem is when we do this and we collect it in water, there's a little bit of water that goes on top of that, and that is known as the water vapor pressure. And so with kinetic molecular theory, right, we talked about temperature, and temperature means average translational kinetic energy. So over a temperature, there is a range of molecules with kinetic energy. Doesn't mean they don't all have the same kinetic energy. There are some that have really high kinetic energy, and there's some that have low kinetic energy. And there's a certain fraction of water molecules at a certain temperature that have enough energy to break away from the liquid. So what keeps water a liquid is the attraction that water has for itself. But there's a small fraction that actually has enough energy to break away, and then that water vaporizes, and actually then some water condenses while the one vaporizes. That's known as a dynamic equilibrium. So, but there is a small percentage of water molecules that has enough energy to then leave the liquid phase and go to the vapor phase. And in a closed container, it's gonna the fraction is gonna stay constant at a given temperature. So let's do this, and this is the same as a combination, like a mixture of gases. So hydrogen class was collected over water at a total pressure of 758 millimeters of mercury and a temperature of 25 degrees Celsius. What is the partial pressure of hydrogen in the gas? So we look up the partial pressure of water at 25 degrees Celsius, and it's 23.8. So that means the total pressure of it, and you would get the pressure just from a barometer, and the total pressure then is going to be the pressure of the hydrogen plus the pressure of the water. And this is, of course, only if it's over a water surface. So whatever liquid it is, if you do it over alcohol, it's going to be the partial pressure of the alcohol. And so then we have the total pressure is we solve for the pressure of hydrogen. I like to do the math. I do like to do the algebra first. You can do the way order, whatever you want. I would solve for pressure of hydrogen. It would be total pressure minus the pressure of water, and then plug in the numbers. Oh, I guess they kind of did do that. And then subtract the vapor pressure, and you get 734 millimeters of mercury. And now with the ideal gas law, if you want to go further, you can figure this out, the number of moles of hydrogen. You can figure out the mass of hydrogen. You should know how to do all this stuff. So here is a chart showing the vapor pressure at various temperatures. And this is something that you don't have to memorize. This is something that will be provided to you or you look up. So don't go and memorize this. So gases and chemical reactions. So when we do chemical reactions in the gas phase, we can do them, and instead of giving you masses and these kind of things, we can start giving them to you as in moles, volumes, temperatures, and pressures. And from that, you can figure out the number of moles and then do good old-fashioned stoichiometry. So let's use this as an example. How many moles of ammonia are formed by a complete reaction of 2.5 liters of hydrogen at 381 Kelvin and 1.32 atmospheres? Assume excess of nitrogen. So now this is a limiting reagent problem, so you can do limiting reagent problems with this. But we know that hydrogen is a limiting reactant reagent because of the fact that it tells you that the nitrogen is in excess. So we know the volume, the temperature, and the pressure. R is always constant. And we want to find the moles of ammonia. First thing we got to do is figure out the moles of hydrogen. So using the ideal gas law, PV equals nRT, so that means PV over RT is going to be the number of moles. And so we get 0.11 moles of hydrogen. And then looking at the stoichiometric ratio, there is a 3-to-2 molar ratio between hydrogen and ammonia. So we have to multiply 2 moles ammonia divided by 3 moles hydrogen. And then from that, we get 0.07 moles of ammonia. So, right, you cannot forget anything you learned before. Everything is building up on the other stuff. And so now you cannot forget stoichiometry, because stoichiometry does have interact with gas laws. You cannot forget molecular weights, that we still use molecular weights here. So you cannot do a brain drain. You have to keep all this information in your heads. So with that. So I mentioned this briefly before about standard temperature and pressure. 1 mole of gas at 0 degrees Celsius and 1 atmosphere, this is 22.4 liters. This is standard temperature and pressure for gases, which is weird because we typically do standard temperature for everything else. We use 25 degrees Celsius and 1 atmosphere of pressure. So, and like I said, in Russia, they use 1 bar instead of 1 atmosphere. So this is kind of confusing that we have a different standard for gases than we do for everything else. But hey, if we made everything make sense, I would be out of a job. So, and it doesn't matter what gas it is. So the mole of helium at standard temperature and pressure is going to be the same volume as a mole of xenon, even though xenon is considerably more massive than helium. But the gases, the pressures and number of moles are proportional. The mass is not. So when gases act ideally, the moles and pressures are directly proportional. They don't, and then of course the volumes. These things all work out to be similar. It doesn't matter what the species is. It's just how much, what pressure, what mole, and what volume. This is all that matters, and temperature. So let's look at this here. Calculate the number of liters of gas it forms at standard temperature and pressure when 0.879 moles of calcium carbonate undergoes the decomposition reaction to lime and carbon dioxide. So we're given 0.879 moles, and we want to know the volume of carbon dioxide in liters. So we just do a direct one here. So from the balance equation, there is a 1-to-1 molar ratio between carbon dioxide and calcium carbonate, and then just use the 22.4 volume per mole of ideal gas, and then so 0.879. And this only works at standard temperature and pressures. And using this, we get 19.7 liters. So remember, this you can only do this at 0 degrees Celsius and 1 atmosphere of pressure. So let's talk about other things that are in the environment. Unfortunately, we have air pollution. Air pollution, and this is mainly referring to anthropogenic, so meaning human-caused air pollution. So one of the things, we have sulfur oxide, especially sulfur dioxide, and this can cause acid rain. This reacts with oxygen in the atmosphere to form sulfur trioxide, reacts with water to form H2SO full of sulfuric acid. It can also react, sulfur dioxide can also react directly with water to form sulfurous acid, H2SO3, and that can rain down, cause acid rain. Carbon monoxide, this is just a little more, it can bind to hemoglobin in the blood more strongly than oxygen, and this can cause toxicity from that. Carbon monoxide is from incomplete combustion. So complete combustion involves to CO2. Incomplete combustion is just to carbon monoxide. Ozone, although technically a secondary pollutant, it can be formed. And the upper atmosphere and the stratosphere is normal, and it's great because it absorbs UV light, especially the UVB. But tropospheric ozone, so we're in the troposphere, we this is a bad thing, and it usually results from sunlight on unburned hydrocarbons. So unburned hydrocarbons and sunlight can cause this. Trees also emit hydrocarbons, so it's not like there's no ozone there naturally. Trees do emit hydrocarbons, and other plant life emit hydrocarbons. So there is a little bit of ozone, and it's not from human caused, but it at high levels it can be quite annoying. And nitrogen oxides as well. These are emitted when so in the combustion chamber you can even break the nitrogen triple bond, and then nitrogen can react with oxygen to form nitrogen oxides, and this can also cause acid rain. Doesn't talk about acid rain. And if you've been to Los Angeles, you can see the haze, and then it's from this, and it is also a lung irritant. So what have we done? We've passed the Clean Air Act. So Congress passed the Clean Air Act, and actually the United States, we're pretty good at clean air. We have pretty clean air here. What we don't have is we don't have very good clean water. Europe is much more has much more stringent laws when it comes to water, whereas the United States has much more stringent laws when it comes to air. It also varies state by state, at least for water laws, for instance. And but since the Clean Air Act, and it includes more than just sulfur oxides, nitrogen oxides, and hydrocarbons. And it includes lead, and also particulate matter is in the Clean Air Act. So this is just an incomplete amount here. And there has been a great decrease in the amount of these primary pollutants that have gone down, and from the passing of the Clean Air Act. So, and basically all the large cities have pollutants in them, and you got to be careful. Like for me, spending too much time in the city, sometimes it can affect your breathing. So be careful about where you're at, and so not even, also including outside the United States. So review, we talked about kinetic molecular theory and an ideal gas, what a pressure is, what the gas laws are, combined gas law, coming up to the ideal gas law, and then how mixtures of gases, because under ideal conditions, the gases pressure are just combined together in Dalton's law. And then talked a little bit about gas and chemical reactions, showing that you cannot forget anything we talk about in previous things. You have to remember everything in this class. So, and hopefully for the rest of your life, because that would be the best thing ever, to always know chemistry. And it's the aim of every enlightened person, of course. So this is what you should learn in this the chapter objectives, and also the legal things. And again, thank you for your time.